Hey there, this is Mrs. Sharp, and today we are going to take some video notes as opposed to regular live notes about the cathode ray tube experiment. We are moving on page, well, it's 3 actually of your notes, but it's the second page of notes. About halfway down starts learning target 1.2. So anything from that point all the way until you get to where it says learning target 1.3 is what we are covering. And in this learning target, it says, describe the cathode ray tube experiment and how it helped to discover the existence of the electron in the atom. Also, to describe the gold foil experiment and how it helped to discover the existence of the nucleus of the atom. So we're going from John Dalton's theory, which is basically, if we think of it as a kind of a rubber bouncy ball, no parts or pieces of the atom, to discovering these pieces, which gets us one step closer to our modern atomic theory. So today we're just going to talk about one of these two experiments, and that is the cathode ray tube experiment. And so the question we are asking, our guided question is, what is the cathode ray tube experiment and how did it help with the discovery of the electron? So we know right off the bat that the cathode ray tube experiment is what gave us knowledge of the electron. So the electron was discovered from studies of what are known as cathode rays using what's known as a Crookes tube. And a Crookes tube is pictured right here. And basically a Crookes tube is a vacuum sealed glass tube. But then you can pump into that glass tube whatever gas you are interested in studying. So pump in any gas. So this Crookes tube, or cathode ray tube, they mean exactly the same thing. This Crookes tube is named after an old guy named Crookes. And what they would do is they would take electrodes on either side. So they would hook it up to a voltage source. And they would basically turn on the voltage source, so they would flip the switch, and they would allow electricity to pass from one side to the other of the glass tube. And then they'd change up what gases went inside the glass tube. So they might put neon in there, they might put argon in there, they might try oxygen, carbon dioxide, all number of gases. And so this was the work of William Crookes. He's the one who started with it. So Crookes started, and then a guy named J.J. Thomson worked with it, and also Robert Millikan. We'll talk more about those later. So remember to only write down the things that are important and that you can possibly paraphrase or condense. So this is a picture of William Crookes. He has quite the mustache. And he was first, and that's why the Crookes tube is named after him. J.J. Thomson did a lot of work, and he's responsible for a lot of what we know about the atom and the electron. And then Robert Millikan there kind of even gave us more information, more sophisticated information about the electron in his famous oil drop experiment, which we're not going to talk about. But again, one thing I really want to hammer home is that all of these people continued the work of the guys before him. So Crookes built on Dalton, Thomson on Crookes experiments, and then Millikan on both of those guys before him. So it's a continuous learning experience. Okay, so Sir William Crookes, he played around with this Crookes tube and noted that what he saw, and it says this worked, regardless of what gases were in the tube and what kind of metal was used in the plate. Now, you might be thinking, like, what worked? Well, what you'd see is this ray, kind of this glowing ray that would go across the tube. And what was interesting is that normally, without any interference, that cathode ray would just go straight across. So if I were to take this, I kind of want to get rid of what I just put on here. If I were to take this cathode ray, okay, ignore that picture for a second. If I were to take this cathode ray tube or this Crookes tube, and I'm going to draw a really bad picture. Okay, so here's the cathode ray tube. And here's an electrode, and here's an electrode. And he was to zap it with electricity. What would happen is that a beam would appear and that beam would travel in a straight line across the tube. Okay, and so that was called the cathode ray, and it was a glowing beam that went from one side to the other as long as the electricity was on. And so that's what it means here when it said this worked. What this means is that the beam would show up no matter what gases you put in that tube and no matter what metals you use as the electrodes. So that told William Crookes that it was in every substance. So whatever it was that was causing this ray to appear was in every single substance. So Sir William Crookes and J.J. Thomson started to play with this cathode ray and noticed that if they were to put charged plates or magnets around the cathode ray tube, they could get the beam that they were seeing to change paths. So for example, in this picture here, normally that cathode ray would just go straight across the tube. But when those gentlemen were to take this is a negatively charged plate up here, and then a positively charged plate on the bottom. I'm just putting that because it's a little hard to see what it's saying there. They could get the beam to move, and it always moved towards the positive and away from the negative. Always. And again, that was no matter what kind of metal in the electrodes, that was no matter what kind of gas in the tube. So the electric current was basically deflected, and because a magnetic field only works on matter, they were able to conclude that whatever matter was in this had a charge and it was smaller than an atom, meaning there was a smaller piece of matter than the atom, something with a negative charge. So that was huge and earth-shattering, and a lot of people didn't believe it. It was subject to a lot of investigation and talking about, but that was a really, really big deal. So again, those particles had to have been negative because they always moved away from the negative plate and toward the positive plate. So that's summarizing basically what we just said there. Actually, a cathode ray tube is what is in old school television sets. The televisions with the really big backs have a cathode ray tube inside of them, and when the electrons hit a screen, it actually causes that screen to light up, and these were used in the first televisions. So if you hear someone who's older say, "I'm going to watch the tube," that is actually referring to the cathode ray tube that was inside most televisions when they first came out. So that's why I love Crookes, because I like TV. So what Thomson ended up doing was determine the mass of an electron. So the reason that we know that an electron is about 2,000 times smaller than the smallest atom, or 1/1837th of an AMU, is because of Thomson's work, which he also used a cathode ray tube. So he figured out the mass. And then Robert Millikan later on determined the exact charge, not just that it was -1, but actually in units called coulombs. Coulombs are a unit of charge. So the more coulombs, the higher intensity of the charge. So very important things to nail down information about the electron. We're not going to talk a whole lot about their experiments, but they're pretty sophisticated and wonderful as well, especially Millikan's oil drop experiment. Okay, so here's what we got. John Dalton, solid and indivisible like a ball. Then we move on to J.J. Thomson / Crookes, and here's how our model changed. So instead of a bouncy ball, it would look like a positively charged solid sphere with subatomic particles known as electrons embedded in the surface. So I picture this, if you were to cut this bouncy ball in half, it looks like tacks in a rubber ball. So if you were to cut this in half, you'd have your electrons almost like a chocolate chip cookie. So this whole sphere part is solid and it's positive. And then stuck in there like chocolate chips are your electrons. Now they call this the plum pudding model after a dessert in England called plum pudding, which I think is gross. I think it's much more effective to think of it as the chocolate chip model, but chocolate chips aren't generally spherical, so that's the only problem with my model. But if you think of it as things stuck inside the solid mass, that's what J.J. Thomson was picturing. So the positive part, not in a nucleus yet, we didn't know about the nucleus. It was spread out over this whole solid sphere, and then inside were these little electrons. And again, smaller pieces, which was a big deal. Big deal to find things that are smaller than the atom. There's J.J. Thomson. There's a cross-section, a positively charged sphere with electrons embedded. There's a picture of actual plum pudding, which you should probably turn down if you ever get the chance. And we are going to stop there. So have a great day.